So, welcome back, and we are going to start this lecture by solving the question which we just showed you last time in the last lecture. The question is, water flows up a 0.5 feet tall ramp. Okay. So, this question has been taken from Monsoon, Young and Okishi, but I would like to discuss it because it gives a better understanding of the specific energy and all the concepts that you have read until now. Okay. So, water flows up 0.5 feet tall ramp in a constant width rectangular channel at a rate q. Q is also in feet square per second. You do not have to worry that much about the units, but how this question is solved. So, if the upstream depth is 2.3 feet, so this is the upstream depth. This is the upstream depth 2.3, all right. Determine the elevation of the water surface downstream of the ramp y2 plus z2. Okay. So, we have to determine y2 plus z2, we have to neglect the viscous effect. This is 0.5 feet, all right, and the flow rate q is given as 5.75 feet square per second. Okay. All right. So, do not worry about the any other unit that is given here. All right. So, with this equation S naught L is equal to Z1 minus Z2 and energy loss is equal to 0, that means conservation of energy. The Bernoulli's equation will require that at 2 points we equate y1 plus v1 square by 2g plus z1 is equal to y2 plus v2 square by 2g plus z2. For the conditions that are given, we know z1 is equal to 0, z2 is 0.5 feet. If you go here, you see z1 is equal to 0, z2 is at 0.5 feet, okay. y1 is 2.3 feet, all right. Therefore, V1 is given by small q1 by y1, which is small q1 because was given 5.75, and if you divide it by y1, that is 2.3 feet, it gives 2.5 feet per second. Therefore, the left hand side the value will turn out to be 1.90. y2 is that we do not know, and v2 square also we do not know, but other equations, but other values we know. We have substituted the value of y all in this FTS unit, where v2 and y2 are in feet per second and feet respectively. Now, we also apply the continuity equation, and this will give us a second equation. So, v1 y1 is equal to v2 y2. So, v1 here you see v1 y1, so a1 v1 or v1 y1, because b is constant, the depth, the width is equal to v2 y2. Okay. So, y2 into v2 is equal to, because we know y1 v1, y1 we know 2.3 and v2 also we know, all right. Sorry, v1 we also know, v1 is 2.5. So, this becomes v2 y2 is equal to 5.75 feet square per second. That is another equation that we have got. Now, equation 1 and 2 can be combined to give a cubic equation, all right. If you do it in terms of y, you can find this equation 1 y2 whole cube minus 1.90 y2 square plus 0.513 is equal to 0. Now, if we solve this, we will get 3 solutions. y2 is equal to 1.72 feet, y2 is going to be another value is going to be 0.6838 feet, and this is a negative value. So, of course, we are going to neglect the negative values, right. So, 2 of these solutions are physically realistic, but the negative solution is meaningless. This is consistent with our previous discussion concerning the specific energy. There we also neglected the negative value. The corresponding elevations of the free surfaces are either y2 plus z2 is going to be 1, I mean if we take 1.72 as y2, 2.2 feet, or if we take 0.638 feet, then it will be 1.14 feet. So, actually which of these flows is to be expected? The question can be answered by use of the specific energy diagram obtained from equation 10, which for the problem is. So, for this particular question, if we write specific energy, we have to make specific energy diagram for this equation, all right. This question is more for understanding. Until this point is fine for calculation in numericals in the assignments and exams, but I mean the later discussion is a little intriguing, you know. So, for this particular question, the energy diagram is equal to y plus 0.513 y square is something like this, all right, where E and y both are in feet. So, if we plot a diagram, we will get something like this. For this q, which is 5.75 feet square per second, this is the diagram that we get, all right. We plot, we see that y critical is going to occur at 1.01 meter, the E minimum, everything has been calculated if we plot this curve, all right. So, the diagram is shown on the right hand side. The upstream conditions correspond to subcritical flow. The downstream is either subcritical or supercritical corresponding to the points 2 or 2 dash. So, the values that we have got is either this one or this one, all right, which is very true because this is the same discussion which we had seen in the specific energy diagram. Now, if we note that since E1 is equal to E2 plus Z2 minus Z1 or E2 plus 0.5 feet, it follows that the downstream conditions are located 0.5 feet to the left of the upstream conditions on the diagram. Now, with a constant width channel, the value of q will remain the same. That is true for any location along the channel. That is all points for the flow from 1 to 2 or 2 dash. So, this is 2 and this is 2 dash. I will just take away this. This is 2 and this is 2 dash. That is all points for flow from 1 to 2 or 2 dash must lie along this line. This is just the discussion of this curve actually going on. Okay. Any deviation from this curve would imply either a change in q or a relaxation of one dimensional flow assumptions. To stay on the curve and go from 1, so this is the point 1, okay, the critical would require a reduction in specific energy to E minimum. As is seen from figure of the problem, this would require a specific elevation bump in the channel bottom so that the critical conditions would occur above this bump. The height of this bump can be obtained from the energy equation written between point 1 and C with SF is equal to 0. Okay. So, E minimum is going to be 1.51 feet, all right, and the top of this bump would need to be ZC minus Z1 is equal to E1 minus E min, that is, you see, E1 is going to be E min minus Z1 plus ZC critical, all right. So, ZC minus Z1 will be E1 minus E min, that is 0.89 feet above the channel bottom at section 1. The flow could then accelerate to supercritical conditions as is shown by the free surface represented by the dashed line. Since the actual elevation change shown in figure of the problem does not contain a bump, the downstream condition will correspond to the subcritical flow denoted by 2, not the supercritical condition 2 dash. Without a bump on the channel bottom, the state 2 dash is inaccessible from the upstream condition state at 1. Such considerations are often termed the accessibility of flow regime. Thus, the surface elevation is 2.2. So, because of this discussion, y2 plus z2 is not going to be 1.68 feet, that was there. You see here, if you had followed this description, I mean if you just understand, so this comes to be y2 plus z2 is coming out to be 2.22 feet and not 1.14 feet. Okay. But I am not expecting you to go to such a detailed discussion. Okay. If you have understood, well and I mean fine, otherwise even if you have not understood this particular discussion about the bump and other things, that is also okay, because what you need to know how to calculate the specific energy, the minimum energy, the critical depth, is the flow supercritical or subcritical and other things like that. Okay. So, I think we can proceed now to a topic that is called channel depth variation. So, for channel depth variation, the general assumption is that it is a gradually varying flow, that is dy by dx is less than 1. We have studied this type of flow, gradually varied flow, uniform flow and rapidly varying flow. So, for channel depth variation, we assume that the flow is gradually varying. Therefore, the total head h is given by v square by 2g kinetic energy head plus y plus z. All right, this is equation 11. Then the energy equation becomes, if we assume the total head h1, because there was no loss, and after going to point 2, this h2 plus hl, where hl is the energy loss. All right, where hl is the energy loss or the head loss between section 1 and section 2. The slope of energy line is, so this is the equation, right, or this is the equation. So, we say, if we use this equation here, we say that dH by dx is dHL by dx, because other things, if you see delta H, if you divide by delta x, this equation star equation, then we get dH by dx is equal to dHL by dx, which is equal to SF, because this is SF, right. So, slope of the channel bottom is dz by dx, correct. Z, if z is the height, the datum, you know, so it becomes dz by dx, that is the slope. That is what we had seen, right, in terms of x, and this was the z, that z datum z. So, it becomes dz dx is the slope. Okay, I will just take out this. So, if you go back to this diagram again, so you see this equation and this equation will hold. Now, if you differentiate 11, so equation number 11, this equation with respect to x, what are we going to get? So, dH by dx is equal to d dx of whole h, right, this is h. So, differentiating one term by term, so it will become 2 v by 2 g, so it becomes v by g into dv dx plus dy dx plus dz dx, correct. So, using the slope of energy line and the bottom slope, we can obtain, so dH by dx is also dHL by dx from the previous slide. So, dV dx is the same and this dy by dx is the same, but dz by dx can be written as S naught. All right. What is this value? This is SF, correct. So, v by g dV dx plus dy by dx is equal to SF, S naught can be taken on the left hand side. So, we are able to get v by g dV dx plus dy by dx is equal to SF minus S naught. All right. or this is called equation number 12 in our current slides. Okay. The velocity of the flow in rectangular channel of constant width b is given by V is small q by y, all right. If we differentiate this also with respect to x, we can obtain dv by dx is equal to minus q by y square dy by dx, all right. And if you put back y v, q is vy, right. So, if you put this in this equation, we get this one. So, it will become minus v by y dy by dx, all right. So, if we multiply the above equation with v by g, this equation by v by g, we are able to obtain this equation. So, v by g dv dx from here, and this also by v by g, this will become minus v square by gy dy dx, and this v square by gy is Froude number whole square. So, actually we get v by g dv dx is equal to minus Froude number whole square into dy by dx, correct. I should take down all the ink. All right. So, here Fr is the local Froude number of the flow. Okay. So, here Fr is the local Froude number of the flow. All right. So, equation number 13. So, you see equation number 13 is this. And this is equation number 12. Okay. Proceeding forward, if we substitute equation 13 into equation number 12, we can simply write, see, going to equation number 13. So, first we should know equation number 12. So, this is equation number 12, this value we already know, right. What is that? V by g into dv dx is equal to minus Froude number square into dy by dx, correct, minus Froude number square into dy by dx. So, we know this minus Froude number square into dy by dx, correct. So, if we take dy by dx common, it will be 1 minus Froude number whole square is equal to sf minus s naught, implies dy by dx is going to be sf minus s naught divided by 1 minus Froude number whole square. Okay. So, and this is exactly what we obtain, dy by dx is going to be sf minus f naught divided by 1 minus Froude number whole square. So, rate of change of fluid depth dy by dx depends upon. So, if you look closely at this equation, the rate of change of fluid depth or dy by dx. Now, if you remember in the beginning, we related all the type of flows like uniform flow or rapidly varied flow, gradually varied flow with this value of dy by dx. So, this dy by dx depends upon the local slope of the channel bottom, which is called S naught. It also depends upon the slope of energy line SF, and it also depends upon the Froude number or Froude number Fr. Now, this equation is also valid for channels with any constant cross sectional shape. We derived this we derived this equation for a rectangular channel. However, it is valid for channels with any constant cross sectional shape. All right. So, we have obtained the equation for dy by dx, correct. Now, we will utilize this equation to study different dy by dx's. Okay. So, first thing that comes to mind is uniform depth flow. So, we know that there are several channels are designed to carry fluid at uniform depth along their channel. All right. For example, irrigation canals, rivers, creeks, and uniform depth means the rate of change of y with respect to x is equal to 0 from equation number 14. So, if dy by dx is equal to 0, that means it is a uniform channel, and this can be made by adjusting the bottom slope. Bottom slope is z naught, because if we are going to design say an irrigation canal or something, we can obviously change the angle of the the slope of the canal. It can be made by adjusting bottom slope such that it equals the slope of this energy line. Roughness can be known, and we can calculate SF. So, if SF is equal to S naught, then we are going to have uniform flow conditions, and then this y which will correspond to this uniform depth flow is called normal depth, and it is denoted by y naught. Okay. So, important thing to note is that the y which corresponds to a uniform depth flow is called normal depth, and it is denoted by y naught. Normal depth. Okay. So, now this is a cross section, all right, and we are seeing the control volume for uniform flow in an open channel. You please, because we are going to derive this. So, if you look at this figure very carefully, you see this is the uniform section 1 here. This is a uniform section 2, F1 is the force which we are going to calculate, hydrostatic force, V1 is the velocity, here depth is y and y1 and y2, but since this is uniform depth, y1 is equal to y2, right. This is the control surface given by this one, okay, and this is the, if the bed shear stress is tau w, okay, and this theta is the slope, the angle of the bed slope. If the weight is w, one of the components will be acting perpendicular to the surface, and one will be acting along the surface. So, using the force balance and continuity equation, we are going to derive something now. All right. So, let us go and see. So, if we apply the x component of momentum equation on this control volume, okay. So, what we are going to see is sigma Fx, that the net force is going to be rho q V2 minus V1, all right, mass flux into V2 minus V1. V2 is the velocity here and V1 is here, all right, and that is going to be 0, correct, because V1 is equal to V2 in uniform flow, all right, because we have taken the same y1 is equal to y2. So, the sum of the forces is going to be 0. There is no acceleration of the fluid, and the momentum flux across section 1 is equal to that across the section 2, all right, implies there is a horizontal force balance given by Fx is equal to 0. So, simply writing F1 minus F2, F1 is the force from section 1, hydrostatic force, F2 is the force that is the force from the other side, that is section 2, all right, because the force acts normal. So, it will be in the opposite direction at F2. If the shear stress at the bed is tau w, that will be acting against the flow. So, it will be in the negative direction, and the weight component of sin theta will be in x direction, and that will be towards the flow direction. Just taking you back to this, you see here F1 minus F2 minus tau WPL, and this is the component this is W sin theta, that is supporting the flow. Okay. This is the equation. All right. Now, we need to know what F1, F2 and other parameters are. So, again rewriting the equation, F1 minus F2 minus tau WPL plus W sin theta, and this is equation number 15. Here F1 and F2 are hydrostatic pressure forces, as we have already told. Okay. W sin theta is the component of fluid weight acting down the slope. All right. Tau WPL is the shear force on fluid. This acts up the slope, trying to slow down the flow. This we have already talked about. This happens because of the viscous forces. Since y1 is equal to y2, flow is at uniform depth, right. So, that means F1 is equal that at uniform depth, F1 is equal to F2. All right. If y1 is equal to y2, F1 is equal to F2, correct? True. So, if F1 is equal to F2, this gets cancelled out. So, tau WPL will be W sin theta, correct? So, tau W can be written as W sin theta by P into L. Okay. So, here theta is very small, that means bottom slope is very small. Therefore, sin theta can be written as tan theta, and that can be written as bottom slope S naught. So, we can simply write tau W is W S naught divided by P into L. Okay. So, instead of sin theta we have written S naught. Now, if we put the weight as gamma A into L, so weight is gamma A into length L, and if we say now we have defined something called hydraulic radius, which is called A by the parameter P. Okay. P, if you see, we have always constantly been writing about P, and you would be wondering what that P actually is. All right. Right from the beginning. So, you know, the shear stress tau W will act on the entire perimeter, where of which all parameters, that are the parameters which is wetted by the liquid. So, all those area where the water is, right, because the, so that is called the wetted parameter P. Okay. So, the parameter or the length across the entire, that is called the perimeter, which is you know wetted by the liquid. So, if we put this term, so tau W will be gamma A L S naught divided by P into L. So, L and L can get cancelled, and we have defined already A by P, this A by P as RH. So, we can simply write gamma RH into S naught for uniform flow. So, shear stress will be gamma RH S naught. All right, and this is an important equation, that is called equation number 16. Right. Okay. So, open channels are actually mostly turbulent, okay, and the Reynolds number lies fully in the turbulent regime. So, here what we are going to do, and actually we are going to see the analogy from the pipe flow, which we will actually study as well. So, for very large Reynolds number, friction factor F for pipe flow is independent of Reynolds number. That is what we know. Okay. So, for very large Reynolds number, friction factor F for pipe flow is independent of Reynolds number and dependent only upon the relative roughness epsilon by D. and the wall shear stress is proportional to dynamic pressure rho v square by 2 and is independent of the viscosity. We know this from pipe flow, and we as in the scientist community had applied this analogy to open channel flow. Okay. So, using this analogy we can say that tau w can be written as k into rho into v square by 2 g. Okay. K is a constant, okay, and it depends upon the pipe roughness, but this is just an assumption. So, assuming similar dependence for high Reynolds number in open channel flows, equation 16, you see this equation 16 here can be rewritten as, this one we already found right hand side of equation, left hand side we substitute by k rho into v square by 2, and we get something like v is equal to c, another constant c. So, we write gamma by k rho 2 gamma divided by k rho whole root as c. Okay. And this equation is the Chezy's equation, and c is called the Chezy coefficient. Okay. That is an important equation. So, v, the velocity can be written as c under root r h s naught, where r h is the hydraulic radius. It was developed by a French engineer named Chezy while designing the canal. C is generally determined from the experiments. Now, you can find the dimensions yourself. Okay, you have done the dimensional analysis. If somebody is not able to, you can ask that to me in the forum. However, is this all right. So, now there is something called Manning equation. We have studied the Chezy's equation. We will be ending the class, this lecture right now, and we will start our next lecture by discussing what a Manning's equation and Manning's number is. Thank you so much for listening. I will see you in the next lecture.